Hi everyone, and welcome to this comprehensive explainer. Today is all about building your ultimate exam survival guide, and really, your foundational physics toolkit. Whether you're actively tackling IGCSE physics right now, or you're just genuinely curious about how scientists manage to measure our massive, chaotic universe with such incredible precision, you are in exactly the right place. We are going to unpack the entire language of data together, and it's going to be a lot of fun. So to kick things off, I want you to picture a physical puzzle. Why is it that a massive iron ocean liner, a ship packed with thousands of passengers, weighing tens of thousands of tons, can just float perfectly safely on the ocean surface, while a tiny, incredibly lightweight pebble dropped over the side sinks straight down into the dark abyss? It's a brilliant question, right? And the crazy thing is, it has absolutely nothing to do with their total weight. I promise you, by the time we finish mastering the fundamental tools of measurement today, you're going to uncover the exact mathematical answer to this mystery. Okay, let's dive into this. Here is our clear 5-step roadmap for today. First up, we'll cover scalars, vectors, and units. Second, the measurement toolkit. Third, volume, density, and displacement. Fourth, accuracy, precision, and errors. And finally, we'll wrap up with mastering significant figures. Starting right off with Section 1, Scalars, Vectors, and Units. This is the language of physics. Before we even think about picking up a physical instrument in the lab, we absolutely must understand the foundational rules of reality. These are the underlying rules that dictate how we describe literally everything in the universe. And the most crucial starting point is understanding the fundamental difference between a scalar quantity and a vector quantity. Think of a scalar quantity as having magnitude, which is just a fancy word for size and nothing else. A vector, on the other hand, has both magnitude and a specific direction. Let's make this concrete. Imagine two cars on a highway. One is moving 30 meters per second to the right, and the other is moving 30 meters per second to the left. Well, they have the exact same speed. That speed is our scalar. It's just the number 30. But because they are moving in totally opposite directions, their velocities are entirely different. Velocity is the vector. It absolutely demands that direction. If an exam question asks you for velocity and you just write down the speed, you're missing half the physical story, and you'll lose points. Now, this brilliantly categorizes the major quantities that you really just need to memorize. On one side, we have our scalars: distance, time, mass, and energy. On the flip side, we have our vectors: displacement, velocity, acceleration, and force. Notice how every single vector physically requires a direction to actually make sense in the real world. You can't just apply a force, right? You have to apply a force in a specific direction. Definitely memorize this list because examiners love testing you on this exact distinction. And while we're talking about the language of physics, we have to talk about units. The essential SI base units are meters for length, kilograms for mass, and seconds for time, along with those key prefixes like milli, centi, and kilo. Now, I want to warn you about a massive, very common trap. Failing to convert your numbers into standard SI units right at the beginning of a problem can completely derail your entire calculation. If an object's mass is given to you in grams, you need to convert it to kilograms immediately, unless the question specifically tells you not to. If the length is in centimeters, switch it to meters right away. Your calculator is smart, but it absolutely cannot save you if you feed it mixed units. Moving steadily along to Section 2, the measurement toolkit. These are our instruments of precision. Now that we have the theoretical rules locked down, let's look at the actual physical tools that physicists use to translate the messy real world into pristine, reliable data. We're going to start with an instrument that honestly intimidates a lot of students, the micrometer screw gauge. When a standard everyday ruler just isn't precise enough to measure something really tiny like the diameter of a wire or the thickness of a single sheet of paper, we bring this out. It has an incredible resolution of 0.01 millimeters. It's basically made of two critical parts. You've got the main scale, which is fixed right there on the barrel, and then you have the rotating thimble scale over on the right. Taking an actual reliable reading with one of these is just an exact step-by-step mathematical process. It's totally designed for cognitive ease. Step 1, you just read the highest visible mark on the main scale. Let's say it's 2.5 millimeters. Okay, step 2, you look over at that rotating thimble scale and you find the exact line that aligns perfectly straight horizontally with the central line of the main scale. Let's imagine it aligns at 17, which represents 0.17 millimeters. Step 3, the easy part. You simply add them together. 2.5 plus 0.17 gives you a final, highly precise reading of 2.67 millimeters. Honestly, if you break it down step by step just like this, it is a guaranteed easy mark on your exam. But here's the thought. What if the instrument isn't the problem? What if we are the problem?
The standard human reaction time is about 0.25 seconds. If you're trying to time a single fast swing of a pendulum with a stopwatch, that quarter-second delay at the start and the stop creates a massive margin of error. So physicists use a really crucial expert hack. We call it the multiple readings trick. Instead of trying to frantically time one single pendulum swing, you calmly measure the time for 10 complete swings, and then just divide that total time by 10. Want to measure the thickness of one tiny piece of paper? Don't even try. Measure a stack of 100, then divide by 100. Doing this drastically reduces human error and averages out all those little uncertainties, giving you beautifully pristine data.
Section 3. Volume, density, and displacement. Time to apply the tools. Okay, so we are now going to combine our measurement tools and our understanding of units to calculate a much more complex derived quantity. And this brings us right back to our ocean liner hook from the very beginning. The secret to why things float or sink isn't about total weight at all. It is entirely about density. Density is defined as mass per unit volume. The formula is rho equals mass divided by volume. It's essentially a measure of how tightly packed a material's matter is within a specific amount of 3D space. Think about that huge ocean liner. Yes, it has a massive amount of mass, but it also has an enormous volume that is largely filled with nothing but air. This makes its overall average density much lower than the water it displaces. That little pebble, however, it has its mass tightly squeezed into a tiny, tiny volume, giving it a density much higher than water. And so, no surprise, it sinks. Now, finding mass is easy enough, right? You just use a balance. Finding the volume of a perfectly regular cube is just basic everyday geometry. But how on earth do you find the volume of a weird, jagged, irregularly shaped rock? You use the incredibly ingenious 5-step displacement method. First, you note the initial volume of water in a measuring cylinder. Second, completely submerge your irregular object into that water. Now, because the water literally has physically nowhere else to go, it gets displaced upwards, rising inside the cylinder. Third, note that new, higher water level. Fourth, subtract the initial volume from the new volume. That difference right there? That is the exact 3D space your jagged rock takes up. Finally, step 5, simply divide the rock's mass by this new volume to calculate its density. It's a beautifully simple, elegant way to isolate the 3D space of literally any complex shape. Let's actually take a quick break from the math for a second for a totally mind-bending fact. Look at this number, 0.69 grams per cubic centimeter. Since pure water has a density of exactly 1.0, we know for a fact that anything less than 1 is going to float. Well, 0.69 just happens to be the average density of the entire planet Saturn. That literally means if you could somehow find a bathtub big enough in the universe, the planet Saturn would float in it like a giant cosmic rubber duck. That really puts the scale and the magic of physics into perspective, doesn't it? Moving into Section 4, accuracy, precision, and errors. It's all about the quality of our data. Now we need to zoom out a bit, because honestly, anyone can take a measurement, but a truly great physicist knows how to judge the actual reliability of their data. And this is exactly where so many easy exam marks are lost. People use these two words interchangeably in everyday life, but in physics, they mean completely different things. Accuracy is how close your measured value is to the true accepted value. Think of hitting the exact center bullseye on a dartboard. Precision, on the other hand, is how close your measured values are to each other, totally regardless of whether they're actually correct. Imagine you throw 3 darts and they all hit the exact same spot way off in the top left corner of the board. Your throws were highly precise, but not at all accurate. In the lab, obviously, we are striving for data that is both. So, how do we make sure our data is high quality? By expertly dodging these very common measurement pitfalls. First up is parallax error. This happens when you get lazy and look at a scale from an angle instead of straight on. You must always read measurement scales horizontally, right at eye level. Second is zero error. This is a systematic calibration issue. It's like having a digital scale that reads 2 grams when there is literally nothing on it. Always zero your instruments before you start measuring. And finally, the meniscus. When measuring liquids in a cylinder, surface tension actually causes the liquid to curve downwards. You must always read the scale from the flat, lowest point of that bottom curve. If you ignore these details, your data is compromised from the very first drop. And finally, Section 5, mastering significant figures, the language of precision.
Moving into our final section, we absolutely must understand that significant figures, or sig figs as everyone calls them, are not just some annoying formatting trick that science teachers force you to do. They are actually the critical language that signals the quality and the uncertainty of your measurement to the rest of the world. Let's look really closely at the zeros in your data, because I guarantee you that's where the exam traps are waiting. In the number 4005, the zeros are sandwiched right there between non-zero digits, so they definitely count. That gives us 4 significant figures. In 0.0032, those leading zeros, they are just placeholders holding the decimal. They do not count at all, giving us only 2 significant figures. But look very closely at 3.00. Because a decimal point is explicitly shown, those trailing zeros absolutely count. They are screaming to the examiner, hey, my instrument was precise enough to measure right down to the hundredths place, so that is 3 significant figures. This brilliantly illustrates exactly what you need to look out for. Which brings us to the ultimate strategy, the golden rule of calculations. Never, ever round during intermediate steps. Keep those messy, crazy long decimals alive in your calculator memory as you work through a multi-step problem. Why? Because if you round halfway through, you introduce these compounding rounding errors that act like a snowball, and they will push your final answer way outside the examiner's acceptable range. You only apply your significant figures to round your very, very final result, and remember, that final answer should almost always match the least precise data point originally given to you in the question. Wow, we have covered an absolute ton of ground today, from the differences between vectors and scalars to the brilliance of the displacement method, from reading micrometers to completely mastering significant figures. You now possess the complete physicist toolkit to accurately measure, record, and make total sense of the incredibly complex physical world around us. So think about it for a second. How much does density and precision dictate your everyday reality? Let me leave you with this final, slightly weird thought to ponder. If you could magically alter your own density right now without changing your mass, would you choose to dramatically expand your volume and float up among the clouds like a giant human hot air balloon? Or would you compress yourself down, getting super dense, to sink and walk perfectly safely across the ocean floor? It's kind of a crazy thought, but hey, it's all just physics waiting to be measured. Keep asking big questions, keep measuring carefully, and I'll see you all in the next explainer.